Okay. So we're starting by taking out yesterday's note sheet. It shows how far we got in learning about the light-dependent reactions of photosynthesis. And we're going to quick review before we move on. Okay, here, just take this one. But don't write on it. Okay. So what we're going to do is, first of all, let's review. So remember at the top, first of all, what am I looking at? What's this? The thylakoid membrane, that's the part that it is, okay? And that, remember, is in the chloroplast. And so we have the reactants going in are light and water, right? So light goes in to photosystem 2, and which is also called P680. It energizes an electron through this electron transport chain, and as the electron is losing energy, that energy is being used in this proton pump to create a concentration of hydrogen ions inside of the thylakoid space. And then this electron that was energized and therefore lost from the reaction center where the chlorophyll is going to be replaced because the Z complex, which is attached to the photosystem, is going to oxidize the water, which means essentially splitting it, and it's going to remove an electron, leave a hydrogen ion in the stroma, and release oxygen as a waste product. Okay? So that's where we are. So what we're going to do now is talk about what happens next. So we left a space here for a reason, and the reason we left a space here is because there is another photosystem that is over here, and we're going to call it, conveniently, photosystem 1, which comes after photosystem 2. Do you remember why I said that they're named that way? Because of when there's the historical reasons. It's nothing to do with anything science-y, really. Okay, so this is photosystem 2, or photosystem 1, see, even what I want to say it the other way. Photosystem 1 has a similar structure in that it has a reaction center, which I'm going to shortcut the word reaction, and then center. And there's also chlorophyll A in the reaction center, but it's a slightly different chlorophyll A. It's called P700 instead of P680. Guess why? It's the wavelength, right. The wavelength that is most absorbed is the 700 nanometer wavelength. That's why. And it also has all the pigment, different types of pigments in there that help to direct or funnel the incoming light. So we've got light coming in. I got to draw that too. All right, so here's our light coming in. So the sunlight is hitting all of it. So this is technically all happening at the same time. Okay, so the light goes in and it gets funneled to the reaction center. And in a similar fashion to photosystem 2, an electron from the reaction center is energized. So the electron is energized, and this time it's going to go to another structure, which is actually an electron acceptor molecule, and it is called NADP+. And fortunately, for our purposes at this time, you don't really need to know a whole lot about that molecule other than it's a big electron acceptor molecule. Okay? And what happens when this accepts the electron, it is then energized, and then what it does is it combines with the hydrogen ions that are there, and it creates an energy molecule, which is NADPH. I'm going to kind of draw little wavy lines because that means it's energized. I have red energy lines. So this is an energy carrier. Okay, so this is an energy carrier, and similarly to the way ATP is an energy carrier. So I guess I'll go ahead and put that squiggly around my ATP because that means it's storing energy. Now, when this reaction center loses its electron because it's energized by light, where do you think the electron to replace it comes from? Look here. Electron went in here and nothing came out, right? So that's where it's going to come from. And there's actually another stop and sort of another electron transport chain, sort of a mini one, but it doesn't have any integral proteins in it, so we're not going to draw it. So we're just going to basically show that electron from here is what replaces the electron in the reaction center. Draw a little arrow so you can see the direction better. Okay? Want me to blow any of that up? Got it? Okay. That's really, so what do I know about these two molecules that I made? They hold energy. So these are going to become important, and they're going to take us to our next phase that we're going to be learning about next week, and that is called the light-independent reactions. Sometimes they call the dark reactions, although they don't have to happen in the dark. So that would be the ATP, and I kind of leave myself enough room here, so I'm just going to kind of draw it. So the ATP, I'm going to make like a big old brown arrow here, and the NADP, I'll make kind of a giant arrow, and those are going to go to the next phase, which is light-independent reactions. So those are going to, that's part 2. Sometimes it's actually called phase 2 of photosynthesis. So this is the completion of the light-independent reactions, or phase 1. Okay? So let's double check to make sure that we understand how everything that we drew relates to everything on our note sheet. Okay? And the first thing that I noticed when I was looking at this note sheet is that, look, we didn't look at the overview yesterday, so we'll look at it today. And it says the machinery is located in the walls of the thylakoid. Well, they're not really walls, right? It's a membrane, so let's just call it what it is. Let's cross out walls, and write membrane, because that's what it is. And so we already saw that the pigments were energized with the light being absorbed, and that the water was split. We talked about that already, trapping the hydrogen ions inside the thylakoid. And then we generated ATP. That's the overview. And then we talked about the Z complex yesterday. And then we talked about photosystem 2 yesterday. And we talked about chemiosmosis yesterday. Except we didn't talk about F, which we now can talk about, which is the electron which has released energy is passed to photosystem 1. So we saw that today. And then in photosystem 1, we see that it becomes energized, and it charges its electron and loses the high energy electron. And then the electron that is lost is actually trapped by the NADP to become NADPH, which is then going to transfer that energy to the light-independent reactions. The other thing, there's a term in here that you need to be aware of, and this is described as a non-cyclic photophosphorylation. So we are phosphorylating the ATP, and it's non-cyclic since we're not recycling the electrons. They're moving along and going on and not coming back. Okay? So cyclic would mean that we're something, either a substance or electron or something is constantly being recirculated, and it's not. So that's why it's considered non-cyclic. So one of the things that you might hear in future AP type questions, even in like the overall test, is for you to be recognizing different types of systems, the ones that are cyclic and ones that are non-cyclic as well. So that's something to be aware of with that. Okay, do we have any questions on that so far? Okay, so we're going to change gears, and what we're going to do is we are going to talk about the lab. Did I give you guys a lab handout yet? All right. I will do that. Yeah, I did send it to you.